Hello, welcome to MATH336 Ordinary Differential Equations. I'm your professor, Nathan Krislock. And I'm going to start by giving a short video, just an outline of the class. And then the next video will be the first section of the textbook. So let's get started. So ordinary differential equations. So there's some words here that we need to explain. A lot of words when you look at the course outline. Let's start with ordinary differential equations. So what does this mean? So let's just make some space here. Move this stuff out of the way for now. So what's interesting here, so I guess we know equation. An equation is a mathematical equation. So something is equal something. Maybe it involves some variables, and maybe you want to solve for those variables. So the word differential is in there because these equations that we're dealing with in this class are going to involve derivatives. So that's why we call these differential equations. But the most curious word here is the word ordinary. So why not just call this class differential equations? Well, the reason that we make an important distinction here with ordinary is because there's another area of math of differential equations called partial differential equations, or PDE. So partial differential equations, maybe I'm just going to abbreviate this. It's a lot of letters to write. So partial differential equations, these are equations with partial derivatives. So these have partial derivatives instead of just ordinary derivatives. And it turns out that these types of equations are more advanced and more difficult to deal with. So, but let me just give a few examples of partial differential equations. So, for example, we can have the heat equation. The heat equation is going to tell us how the temperature in some body is diffusing. So if a hot part is near a cold part of this object, then the hot part will get colder and the cold part will get hotter because they're spreading the heat out between them. So how does the temperature of this object change over time? So this is governed by the heat equation, which says that if you have U represent the temperature of the object at a certain point, so we'll just do a two-dimensional heat equation. So we have some sort of a object here, and it has temperature. Some parts are hot, some parts are cold, and we have a temperature for each point in this object, which we represent as the XY point in this object. So how, and then of course the temperature is changing over time. So as we go along, the temperature is going to be changing. So this U of X, Y, T, this is going to be the temperature at the point XY at time T. And what is the heat equation? So the heat equation is this partial differential equation. So notice we have three variables here. We have X, Y, and T. So this is like multivariable calculus that we're doing now. So with multiple variables, we have partial derivatives as opposed to ordinary derivatives. So the partial derivative of u with respect to t, so this is measuring how fast the temperature is changing with respect to time. And the heat equation says that this is going to be proportional, so it's some constant here, times the sort of a measure of the how fast the temperature is sort of changing around this point. So kind of like a concavity. You remember in calculus, we talk about concave up and concave down, and this, how concave a function is depends on its second derivative. So this sum of second partial derivatives is sort of measuring like how steeply this function is sort of, or how concave it is. So if it's very concave up, then that means it's very hot at this point and is sort of cooler nearby. If it's concave up, then I guess we're talking about it being cooler at this point and sort of warmer all around it. So if it's concave down, then that means that this point in the middle, which is hotter, it's going to cool down. So this expression is sort of saying that the temperature will cool down, and the rate at which it cools down is going to be proportional to sort of this measure. All right, so this is the heat equation. So involving partial derivatives. Another really popular example of a well-known partial differential equation is the wave equation. So the wave equation, in this case we have, so let's just do like a two-dimensional or a one-dimensional string. So we have some sort of a string, like a guitar string or something, and it is vibrating. So, you know, maybe part of it is going up and part of it is going down, and it's sort of vibrating. So I'm just showing you, you know, one instance in time, how the string looks at one moment in time. But imagine that we're sort of animating this, and the spring is, or this string is like vibrating rapidly. So how can we talk about this string vibration? So we can let U sort of represent the, we'll let it represent the displacement, sort of displacement from the x-axis. So the displacement, it could be positive or negative, of the string at point x, so it's a specific point along this x-axis, and then at time t, like that. So a vibrating string. So that's what we're looking at. So we're looking at, for example, a vibrating string. So a vibrating string, and what is the wave equation? Well, it says that the acceleration, so the second derivative of u with respect to t, so the acceleration is going to be proportional to, again, it's the same expression as above. So it's actually the sum of partial derivatives, second order partial derivatives. So that is what governs the acceleration of this string. It has to do with sort of, I guess, some sort of measure of concavity of this string. Oh wait, sorry, this is only has one variable. Actually, this equation is much nicer. So I wrote down that like a two-dimensional wave equation, like waves on the ocean or something. So actually, for this example here, it's actually just simply this. But anyway, now you know what the general wave equation is if it was two-dimensional. So yeah, so these are partial differential equations. And when we say ordinary differential equations, we mean that we're looking at a simpler situation where we're measuring something that's a function of just one variable instead of multiple variables. So this has two variables and this heat equation has three variables. Ordinary differential equations will only deal with single variables. So let's look at that. So an ordinary differential equation, this is a differential equation. Well, I guess I could just say it's a, because I'm going to say it in a bit. This is an equation with only ordinary derivatives. And it's really the starting place for talking about differential equations. These are much simpler than the partial differential equations. So in this case, we'll only have a single variable. Usually it's time. So there's going to be like a dependent variable like u, or sometimes it's called other things. And then there'll be an independent variable, which is usually time. It's a good way to think of it, but we'll use other things as well, not just time, but we'll also use, we'll use x as the independent variable very often. So let's look at an example of a, let's see, just move this out of the way. So let's look at an example of an ordinary differential equation. So this is very timely example. With the coronavirus pandemic that we're in right now, we've been thinking a lot about how disease spreads through a population. So we can actually model this. You know, it may not be the most accurate model, but it's a mathematical model which somehow measures the fraction of people infected with a contagious disease. Okay, so what is like a good model here? So, well, so often they talk about like initially when the pandemic is sort of starting off, when this fraction is quite small, it appears that the rate at which it's changing is proportional to the number of people who are, or the proportion of people who are infected, right? So it sort of follows this this model, but it turns out this isn't a very good model as time goes on. As time goes on, we don't see that this this growth is exponential anymore. It sort of slows down and then eventually comes to a halt once, you know, a large enough fraction of people are infected or are vaccinated, as another way to prevent yourself from getting this disease again. So maybe this is not such a good model. So so this would lead to an exponential. So this is exponential growth. Exponential growth. Not the best model. So a better model is what's called logistic growth. So the rate of change of the the fraction of people infected with this disease is proportional to the number of people who are infected right now times the number of people who are not infected. This is sort of a better model because it says that, you know, the more people who are infected interact with people who are not infected, the more the disease spreads. So multiply p times 1 minus p. It's a way of you know, measuring how often these two groups of people will be, or how likely they are to interact with each other. If p is only 1%, then 1 minus p is 99%. So 0.01 times 0.99, this is a small number. So it's less likely that the number of people who are, the number of these, you know, interactions is fairly low. However, when p is like 50%, then sort of the probability or the chance of having an infected person and a non-infected person interact and possibly transmit the disease is much more. So, so for example, when so maybe we'll just do like, you know, k equals 2 or something. So k equals 2. I don't know. I mean, you have to figure out what this k is depending on the data, but let's just say it's 2 for argument's sake. So what if p of t at some time, I don't know what time exactly. So p of t is 0.01. Then what does that mean? It means that the rate of change, so I just have to pull up I guess I could do this in my head. So it's going to be, you know, 2 times, and then 99 times 0.01. So that'll be 0.0099. All right, let me just move this over. It's getting a little too close to the edge of the screen. So let me write this again, a little bit bigger. 2 times 0.0099, right? So that's going to be a pretty small number, 2 times 0.0099, and that's going to be, you know, 0.0198. So it's approximately, not surprisingly, it's approximately 0.02. So that means that the current rate of change of the percentage of the fraction of the population that is getting infected every time period, so this could be like every day, for example, is going to be 0.0, so about 2%. It'll be about 2%. So 2% more every day. So, you know, that could be seen as a lot. So today is 0.01 and tomorrow it's 0.03. So that's sort of the rate of change at that moment in time. But let's look at what happens when like half of the population is actually infected, or I guess contagious would be a better way to think of it. So let's say that we currently have, you know, half of the population, and half are yet to be infected. So then what is the rate of change at that moment in time? So I guess this is much easier to do. So this is just going to be 2 times, you know, 1/4, and that will be equal to 0.5. So that's kind of a lot now. So now we're going really increase quite rapidly. So I mean, in a sense, it means we're going to go from like 0.5 to 1 all at once. So in one time period, we'll have half of the population infected, and the next time period, it'll basically be everybody. Of course, this is all approximate, and you do lose a lot of the reality of what is actually going on by looking at such a simple model. But this is how mathematical modeling works. You try to model a real life situation with a mathematical equation. You solve that equation and you interpret the results and see if they make sense. And if they don't make sense, then you go back to the drawing board and you start again. So you keep doing this until the mathematical model you have is something that you can solve and use, but also that approximates reality pretty well. So that's the idea. Okay, so, oh, and by the way, let me just quickly draw a picture of, what does a logistic curve look like? So this logistic curve is, it's P here, and this is time. So it's going to start, pretty low, like, well, I guess not exactly 0, but it'll go, up to some inflection point, and then it'll approach 1 eventually. So it'll start off like increasing rapidly. So we sort of see that exponential growth initially, but then at some point it reaches this inflection point when it's, and then it sort of tapers off. So that's what the solution looks like. And okay, so that's the logistic growth. Did I write that down somewhere? So this is logistic growth. So this is logistic growth. A much better model of how disease spreads. Okay, so let's move on to sort of discuss the course outline now. So let me just move this up to right about there. All right. So we're going to go through topics in the following order. We're going to first look at a very simple type of differential equation where we only have to worry about first order derivatives. So in chapter 1, we're only going to work with the first derivative. So there won't be any second derivative or third derivative. We're just looking at equations involving the first derivative of some quantity and no higher derivatives. Which typically means that our differential equation can be put in the following form. We can sort of solve for that derivative. And we'll have this derivative sort of in the equation, and we can isolate it. And we know that this rate of change is going to be a function of whatever the quantity x is at that moment in time. And also it'll be a function of time as well. So the previous one that we saw with logistic growth, it didn't actually have time as a variable in the rate of change, but we will see differential equations where it's a function of both the quantity x and also the time as well. So this is the type of equations that we'll be looking at in chapter 1. Now, we'll learn a number of methods for working with these first order differential equations, but there are some, even though they're rather simple, they're only the first derivative, they're still can be challenging to solve some of these equations. So so for some of these equations, we want to turn to numerical methods in order to approximate their solution. So for example, if we have y of t, which is some sort of quantity, that's something, quantity of y at time t, and we have a differential equation which says the rate of change of this quantity with respect to time is given by some formula which involves y and t. So we can do the following really nice idea, which is to use the fact that we know that if you move a little bit from t, so we're thinking of h as being something rather small, we know from like Taylor series, or just the idea that if you have a tangent to a curve, then that tangent is going to approximate that curve pretty well when you just move a little bit away. So the way we write this is we say that y of t is going plus h is going to be very close to y of t plus h times the slope of that tangent. So this is going to be a good approximation for small h. So it has to be small h. Positive. Well, either way, but yeah, it could be negative as well. So positive or negative h, this will be fine, but it has to be small. So how can we then incorporate this differential equation into this approximation? Well, we know what this derivative is here. So this derivative right here, that guy is going to be, we can compute that. We have a formula for that. So we get that y of t plus h is approximately y of t plus h, and then times, we just plug in the values of y at our current time, t, and we plug in t into this formula f, and that gives us a formula for the approximation of this of y at the next step. So you just sort of like step along with small h, and you just get a bunch of approximations for your value of y at different times. Gives us a bunch of data points. We could plot a curve through those data points, and it gives us a pretty good idea of what the solution of this differential equation is. All right. So we'll look at numerical methods for solving differential equations, or not solving them, but like approximating the solution of differential equations. So after we look at that, then we will move on to chapter 2, where we'll start looking at differential equations of higher order. So where we now have derivatives more than the first derivative, we'll have second derivative, third derivative, fourth derivative, and so on. However, in order for us to deal with these more complicated differential equations, we will need to assume something, and what we'll assume is that they are linear. So it means that they're sort of in a nice form, which we'll get into a bit later. But I'll give you an example of such a differential equation that is linear and is a higher order differential equation. It comes up in mechanical vibrations. So for example, when there's an earthquake and the buildings sway, or the bridge sort of sways as well due to the wind and cars driving over it. So lots of different things can produce vibrations in different objects. So a very simple way to represent these mechanical vibrations is to think of having some mass here, and it's connected to a spring, and the spring has spring coefficient K, which sort of measures like how stiff the spring is. And we're currently displacing this mass by amount X. So normally the spring would want to keep the weight right here, and we've pulled the weight we pulled this mass to the right. So this spring is kind of stretched and it's trying to pull the mass back as well. And assuming no friction, this thing will just kind of go back and forth forever. But we're going to add something else in here which will represent like friction, or it could be another type of object like the damper that you have when you're trying to make sure a door closes slowly and doesn't slam. You notice that those dampers will resist you pushing. You like close the door faster, and it will actually resist you more the more you like try to close it. So this is a damper here. So we have a damper, and the damper could be friction, or it could be something to try to prevent vibrations. We have a mass here. We have a spring here. And we're going to say x of t is the displacement of the mass from equilibrium at time t. And we can use a very familiar law which says the force is equal to mass times acceleration. And this allows us to actually write down a differential equation which says mass times acceleration. And there's some work involved here in figuring out what this is, but it's going to be this damping coefficient times the velocity plus the spring coefficient times the displacement. And we could also include some external force as well. So maybe at every time we're sort of like, pushing this mass one way or another, maybe back and forth, kind of like a sine wave force. We're just like going, like a spinning washing machine or something like this. So an external force. And here we have a second order differential equation. And just to mention, this is the external force. External force at time t. And when you solve this differential equation, you'll see things in the mathematical solution that represent, what's it called? I'm forgetting the word for it now. Resonance, where you've seen these videos of a bridge sort of falling apart because the wind is causing vibrations that are resonating, and it's causing the bridge to shake more and more and more until the bridge falls apart. So anyway, this can be observed in the mathematical solutions of this differential equation. The next topic that we'll look at is especially important for electrical engineers. So it is the technique of using Laplace transforms to solve a differential equation. So this is a really remarkable thing. So we'll be able to look at the differential equations we were solving in the previous two chapters. And we'll have this new technique for solving these differential equations, which is really remarkable. What we do is we apply this Laplace transform to the differential equation. And what it produces for us is actually an algebraic equation in the Laplace transform of the solution. So it gives us an algebraic equation. What we do then is, instead of like integrating or using calculus to solve the differential equation, because it's an algebraic equation, we can actually solve it. Maybe I'll just move this over here. So we're going to solve this algebraic equation for the Laplace transform. So it's literally just algebra at that point. So we'll solve it, we'll get that it's equal to something, I don't know what. And then you take that, that thing here, so I'll just copy it over here, just so it's clear what's going on. We take this thing, whatever it is, and we apply the inverse Laplace transform, and that actually just gives us the solution of the differential equation. It's really remarkable. It almost feels like you're cheating in some way doing this. And it turns out in some sense that in the Laplace domain, multiplication corresponds to differentiation in the time domain, and division in the Laplace domain corresponds to integration in the time domain. So it's really, really remarkable, and it allows us to handle differential equations we can't handle with previous methods, such as equations where, for example, someone's turning the light switch on at some point and then turn it off. Again, you can look at these circuits where something's turning on and then off, and maybe it's turning on and off and on and off like that. You can actually solve these with Laplace transforms, and you can't with our previous methods. So that's really cool. And then finally, we're going to spend a little bit of time looking at linear systems of differential equations. And the main thing here that's of interest is that these are important because they allow us to actually convert higher order equations into a system of first order equations. So for example, we can look at the mechanical vibrations that we were just looking at. So let's see if we have an equation that looks like, oh, let me just put 2 in here instead of C. Well, I could put C in. We're not afraid of C. So let's put C in. So C, and then K is the spring coefficient, and imagine that there's actually no external force here. So what we can do is we can actually just say this is a second order equation, and we would like to get a system of first order equations. So we're going to let x1 be x, and we'll let x2 be x prime. And what does this give us? I'll just move this over here. So we'll let this and this. So what do we get? So we get that, so x1 prime, that's a prime. Looks like a 1. x1 prime, that doesn't look good either. x1 prime, there we go. x1 prime is x2. That's what I just said above. And then x2 prime is going to be, well, that's the second derivative of x now. And we have a formula for that. That's going to be negative cx prime, but x prime is x2. And then negative kx, x is x1. So we get this equation. So now look, we have two functions, x1 of t and x2 of t, and we have formulas for their first derivatives. So now we have a system only involving first derivatives, and this chapter 5 is about, well, first learning this technique of how to convert things into systems of first order equations, and then how to solve them. So, and in particular, this chapter is about linear systems of differential equations as opposed to nonlinear. Yeah. So that's it. This has been sort of an overview of the class. I hope it's been useful. In the next video, I will start with section 1.1, and we'll start learning about ordinary differential equations from the beginning. So let me just turn my video on here. Yeah, so I'll see you in the next video. All right, thanks.